I'm trying to get all the videos online. Okay, so here's the deal. Everyone's on a computer right now. I want you to look at this. This is an area that you probably want to pay attention to. Because more than likely, even if you've had general chemistry, you have not had this. And this is not easy. This is a mathematical understanding of bonding, but it's also the most powerful understanding of bonding. Molecular orbital theory really is the most advanced theory in all of chemistry. It comes from quantum theory. It deals with a mathematical solution of the location of electrons and how they form bonds. We're going to talk about cool things in there like bonding and anti-bonding. Anti-bonding sounds a lot like antimatter. What do we mean by antibond in connection to a bond? So everything that we've learned up to this point, we left off talking about delocalization and resonance. All those theories up to this point, Lewis dot structure, resonance theory, valence bond theory, hybridization orbitals, and multiple bonding, all of that fits nicely into a theory, into a box. We need to put that box away, put tape on it, and set it aside. What we're dealing with now is a brand new theory that does not move into that box. This is a standalone theory, it starts fresh. Okay? There's a wall between what we have talked about the first two and today. Molecular orbital theory, or more specifically in organic chemistry, frontier molecular orbital theory gets the symmetric rearrangements and some really neat things that really helps us explain what's going on at a deeper level of chemistry. That's why I love this theory, but this theory can be really gory and difficult. So that's why I really want us to engage today, because I'm really passionate about this theory. It's what I teach in advanced organic chemistry, except to a much deeper level, so we can actually understand how to use this practically in a chemistry lab. So we're coming out of resonance and we're moving into molecular orbital theory. So one of the cool things as a final slide in this whole resonance thing is if you take the benzene ring, that we can draw one form of it this and one form of it doesn't look like that, it looks like this, right? And we drew the circle between those six, that hexagon, and we call that benzene or the aromatic group. What we're doing now is we're going to go from this is the culmination of that, into molecular orbital theory. Now, who remembers what these are called? Who can tell me when I had a hydrogen atom, I said it's a 1s1. What was that? So where the electrons are for what? Of a hydrogen atom. Stay with me, that's really important. Anyway, what? When I said carbon is 1s2, 2s2, 2p2, that is the electron configuration of a carbon atom. What is this theory? Is it atomic bonding or is it molecular bonding? It's molecular orbital theory. Okay? Molecules orbital theory. This is atomic orbitals. So when we talked about the 1s, the 2s, the 2p, these are atomic orbitals. So in the atomic orbital of the 1s, where the quantum number is n equals 1, I can fit 2 electrons in the 1s. In the n equals 2 energy level, I can fit 2 electrons in the 2s, I can fit 2 electrons in the 2px, I can fit 2 electrons in the 2py, and I can fit 2 electrons in the 2pz. So total, I can fit 2, 4, 6, 8 electrons in those 4 atomic orbitals. But here's what we want to ask. What happens when one atomic orbital interacts with another atomic orbital? Oh, when an atom reacts with an atom, it forms a molecule or a molecular bond. That's where the term molecular orbital theory comes from. What's happening when one atom reacts with another atom or brings its electrons in and says, let's go ahead and form a bond. So we're going to move from atomic orbitals into molecular orbitals. Okay? So let's start basic. Let's start with hydrogen. If we start with hydrogen, you'll see that hydrogen is one of those, yeah, sorry. Let's go back for a second. This is one of those cool things. If we draw a good Lewis dot structure for O2, watch this. This is really cool. I forgot about this. This is such a cool introduction part. This oxygen and this oxygen both bring in 6 electrons, so I have 12 electrons, right? So let's draw a Lewis dot structure for oxygen, okay? And here's what we're going to do. We're going to draw oxygen and an oxygen. We're going to put the electrons around it, and we're going to say, are we happy? We have 2, 4, 6, 8, 10, 12, 14. Oh, that's too many. Can't have that many. So this one's not happy, so this one comes in and says, cool. There's a really nice Lewis dot structure for oxygen. Then here's the problem. It looks so beautiful. Everything you've learned up to this point says, that's a great Lewis dot structure for oxygen. And I would come up and go, that is not what oxygen looks like. And that should frustrate you. Because experimentally, oxygen is paramagnetic, meaning if you put it between a poles, and Dr. Lawrence does this in physics, if you put it between a pole, it actually moves to the positive pole, meaning the electrons aren't paired up. And this does not explain that, because these electrons are paired, these are paired, these are paired, these are paired, these are paired, and these are paired. There's no way that oxygen should be attracted to the positive pole of a superconducting magnet or a very high-end magnet. So Lewis dot structures, valence bond theory, hybridized orbitals doesn't work. It fails. We do need a better theory. It is a paramagnetic molecule, but again, that does not explain why, whereas molecular orbital explains perfectly why oxygen behaves the way it does. Why is oxygen paramagnetic, okay? Now, let's talk about this better theory. Here's what we have to remember. This is our working diagram. The reason why I've done yellow and red on this is I can't underscore enough, we're talking about a bond. So here's the way this works. I'm going to bring in a hydrogen, and it's going to be a 1s1 atomic orbital electron. I'm going to bring in another hydrogen, 1 hydrogen. It's a 1s1 atomic orbital. So if I bring in a 1s1, oh, that's the atomic orbital. That's what hydrogen is, 1s1. I know that. I've memorized that. And I bring in a 1s hydrogen. Notice, mathematically, I have 2 possibilities of how those particles can come together. I have what's called a constructive or a destructive solution to bringing those atomic orbitals together to form molecular orbitals. So let's talk about a little bit of math. What happens in math if I take 2 sine waves and add them together? What does it equal? Come on, you guys have all had SOHCAHTOA. Yep. Same phase. What happens? They doubles the amplitude. So it looks like this. It's going to be the same wavelength, double amplitude. Okay? What's that? So this, I still can't hear you. Yeah, we're not there yet. Yeah, hold on. So this is what we call constructive. We call this a constructive solution to bringing 2 waves that are in the same phase together. This is what we call bonding. Okay? That is a bonding solution to those 2 waves. So if this electron is a wave and this electron is a wave, I add them in the same phase, they add favorably or constructively. We call this bonding. We tracking? This is where this becomes mathematical. This is the only math we're going to do. We're not going to have you solve it. I just want you to see where this comes from, because it's brilliant. If I have a wave that looks like this, and a wave that looks like this, what happens? What is it? You got it. So they cancel out, and it looks like that. Okay? So these electrons can come together in a constructive, what we call constructive interference or destructive interference. Okay? This is destructive. And this is what we call anti-bonding. And we designate it with an asterisk. Okay? So let's review. If I have two molecular orbitals, excuse me, two atomic orbitals, I have an atomic orbital here, 1s1, and I have an atomic orbital here, 1s1. Again, these are atomic orbitals. So atomic orbital, atomic orbital. How many atomic orbitals do I have? 2. Since I have 2 atomic orbitals, I have to have 2 molecular orbitals. I can't just get rid of an orbital. I have atomic orbital and I have atomic orbital. Therefore, I have to have 2 molecular orbitals, but they have to be different. One, and this is all energy, just like we've always done. This is energy. Energy increasing. One is constructive. It likes the other one. So we put that lower in energy. Okay? And you can see that up there. We call this, and that's what this comes from. This now becomes the sigma 1s bonding orbital, atomic orbital. This is sigma 1s. Okay? That is the constructive interference between 2 electrons in a favorable way. We call it bonding. But I have another mathematical solution to this. If those 2 orbitals come together in a constructive way, or excuse me, destructive way, they go into what we call an anti-bonding, or in this case, a sigma 1s star anti-bonding orbital set. Anti-bonding is noted by an asterisk. So with that, if I have 2 atomic orbitals, I have to have 2 molecular orbitals. The molecular orbitals cannot have the same energy, therefore there's going to be one that's constructive and one that's destructive. The one that's constructive is favorable in energy. It's lower in energy. There's something about when this electron heads over to this electron and this electron heads over to this electron, they go, oh, hey, there's something really cool if we do this. And there's something really sinister or really bad if we do this. So that's why sigma 1s is lower in energy than sigma 1s star, or sigma star 1s, depending on how do they designate it up there. Yeah, they do the star up there, that's fine. Okay, so that's a bonding and an anti-bonding probability of those 2 electrons coming together. Are we tracking? A 1s atomic orbital, a 1s atomic orbital, when they come together, they can either go to a bonding or an anti-bonding mode. Yes?
If you go from sigma 1s star to sigma 1s, you have to go to the 1s separated first.
First. You got it. First.
You can't jump directly to that.
No. Because again, everything's going to go low energy first and populate to high energy. Yeah. Okay? Are we tracking? Yes?
Does it have to do with the orbital spin? Is that how you get?
No. Don't think of that. Again, this is mathematical. You don't want to bring too much out of the box from before. Okay? It literally is, if I bring 2 waves together, because remember, electron can be thought of as a wave, particle or a wave, right? If I think of it as a wave, there's two ways to bring that wave together. I can either bring it together constructively or destructively. And that's it. It's literally, this is a very mathematical, it's the most gory math that typically chemists do until we get to a little bit of quantum theory or quantum mechanics. Then it gets much more math. Okay? Now notice this. In the anti-bonding, it sets up a destructive interference, and it sets up a node. So you can see the node up there, okay? The nodal plane says there's 0 probability of finding any electrons here. Again, because it's destructive interference. So here's what I can underscore enough. If I start with 2 atomic orbitals, I have to end in 2 molecular orbitals. I have a constructive and destructive possibility. One is bonding, one is anti-bonding, okay? So here's what happens when 2 hydrogen atoms bring their atomic orbitals together into a molecular orbital. How many electrons does a atomic orbital hold? How many electrons can I fit in an atomic orbital? 2. Likewise, I can only fit 2 electrons into a molecular orbital. A molecular orbital can only hold 2 electrons. Okay? We tracking? So here's what happens. When this electron and this electron come together mathematically, they say, oh, I have an open atomic orbital with constructive interference. Let's go ahead and let's make a molecular orbital and put them down there. Okay? So with this theory then, I can calculate the bond order. So bond order then is going to be bonding electrons minus anti-bonding electrons divided by 2. Okay? That's very important. I talked about bond order last Friday. Single bond has a bond order of 1. Double bond has a bond order of 2. Triple bond has a bond order of 3. So if bond order equals bonding electrons minus anti-bonding electrons divided by 2, notice this. I am 2 minus 0 divided by 2, which equals 1. Hey, that's interesting. What do we predict and what do we see experimentally between 2 hydrogens? We see 1 bond. Okay, so the theory holds. The theory is predictable. Hydrogen, if it's not a hydride or a proton from an acid, it always is a divalent molecule, okay? So it's going to be H2. All right, we tracking so far? Any questions on it before we start? We're going to complicate this, and it's going to get really complex. You know.
So when you're in the context of a formula, the antibody,
Say it one more time.
in the context of the formula, the antibody electrons, like how do you determine that? Because hydrogen has 0.
Yes, you'll see that. We're going to go to helium next.
Okay.
Yeah, we're going to build. I'll show you how that works. Hunter, do you have a question?
Yeah, so the equations for only enthalpy, they still carry over.
Remember, this is theory. Enthalpy is actually, I want to say it's real. It's measurable. This is all.
But you can't like measure the difference in
No.
and then like
We do know that anti-bonding is slightly higher in energy than bonding. So for example,
there's no specific like,
no. We do know, and I have it drawn. We do know that if you take this line, right, if you wanted to draw it like correct, it is, this anti-bonding is going to be higher than that. So if I drew it up here, probably a little bit more accurate, and I can just exaggerate that. We do know that anti-bonding is higher than bonding is lower. And then that's about it. Here's what's going to be practical about this theory. We're going to be able to predict the magnetism of these diatomic. That's what becomes very cool about this theory. We see why it is that oxygen is paramagnetic. Okay? Stay with me, we're building on this. Okay. 2 atomic orbitals, 2 molecular orbitals. We tracking? If I start with 2, I have to end with 2. I can't build another one, I can't take one away. If I have 2, I have to have 2. There's just 2 solutions. One's good, low energy, one's bad, high energy. That's it. Okay? So let's go to our next atom on the periodic table and let's predict the bond order for He2. Now, does anybody remember what I said about helium? That's really special about helium? It's a noble gas, super happy, has all of its electrons in the n equals 1 energy level. What's the ionization energy for helium? Low or high? What is it? Really high, right? Does helium want to give up an electron? Does helium want to gain an electron? Helium is one of the only atoms on the periodic table that's never been observed to make a bond. So what would we expect for He2? Probably not going to happen. So let's see if molecular orbital theory can help us with this. So if I bring in helium, and I say helium now, helium, I bring in 1 helium and 1 helium. Helium has an atomic orbital of 1s2, correct? We've gone through atomic orbitals. We're comfortable with atomic orbitals. So helium says I'm 1s2, and this helium says I'm 1s2 as well. So helium brings in 2 atomic orbitals. So if I bring in 2 atomic orbitals, how many molecular orbitals do I have to have? 2. So now I've got 2 molecular orbitals that can only hold 4 electrons, and I have 4 electrons. So helium says, okay, I'll come and join. Let's put 2 in bonding. Oh, well, we have 2 to go, so we're going to have to force those up here into anti-bonding. So what's the bond order of He2? What is it? 0. 2 minus 2 divided by 2 is 0. Molecular orbital accurately predicts that the bond order between 2 helium atoms is 0. There shouldn't be any bonding. And that's exactly what we see experimentally. We do not see bonding between helium. Okay? Questions on that? Because we're going to keep going. Guess where we're going next? Lithium, because it's number 3. So, when we get to lithium, notice what happens with lithium. Lithium is like helium, but it has an electron in where? The 2s orbital. So we have to draw the 2s orbital. So 2s and 2s. So lithium is 1s2, 2s1, 1s2, 2s1. So lithium's atomic orbitals look like this, right? It's a 1s2, 2s1. So now how many atomic orbitals am I bringing together? 4. 2 and 2. If I'm bringing 4 atomic orbitals together, how many molecular orbitals do I have to have? I have to have 4. I can't create or destroy orbitals. So I'm going to have a bonding solution and an anti-bonding solution. So this is going to be my sigma 2s. This is going to be my sigma star 2s. And when that electron comes in, it says, hey, mathematically we have a probability. We can go there or we can go there. Okay. So lithium puts its electrons into a bonding first, okay? And since I have 1, 2, 3, 4 atomic orbitals, I have to have 1, 2, 3, 4 molecular orbitals. Since I have 2, 3, 4, 6, some good math right there, okay? 2, 3, 5, 6, I have to have 6 electrons in my molecular orbital solution, so it's 2, 4, 6. But notice, it's okay to put 2 electrons in a 1s anti-bonding. It's okay to put electrons in an anti-bonding if I have another orbital higher in energy. Remember, this is energy. It's increasing. So I filled my 1s with 1s bonding, 1s anti-bonding. I still have 2 electrons in a higher 2s orbital. They go to the lowest energy possible, which is the sigma 2s bonding. Oh, that's kind of cool. Yeah. What if you have what? Oh, we'll get there. We'll get there. We'll get there. Oh, it's fun. It's going to get so fun. So watch what happens here. How many electrons do I have in bonding orbitals? 4. 1, 2, 3, 4. Therefore, the bond order for lithium should be 4 minus, how many do I have in antibonding? 2. 1, 2, divided by 2 equals what? 1. Hey, the bond order between 2 lithium atoms should be 1, and it does. Lithium forms 1 bond with another lithium. They form dilithium crystals if you want to bring in Star Trek. So we see that molecular orbitals predict accurately what we see experimentally. Okay? And what should we expect for beryllium? Well, watch what happens with beryllium. Beryllium is 4 electrons. 1s2, 2s2. I have to bring all those together. So beryllium looks like this. So where do I put 4 electrons? Or excuse me, where do I put 8 electrons? Yeah, they got to go up in the anti-bonding 2s. So they go there. So what's the bond order for beryllium 2? 0. And that's exactly what we see. Yes?
So this doesn't predict how many bonds there will be between different atoms, only between the same atom?
No, we'll get there. That's what Hunter asked. No, we'll get to different atoms. Right now, we're talking 1 bond between the same. Yeah, just to set the foundation. Okay? You sure?
Sulfur would be 8, right?
Oh, wait for sulfur. We're not going to do sulfur. Just wait. It gets so complex when we get down to sulfur.
Yeah.
Because watch what happens when we jump over to boron. Now this is where it gets fun. Everyone, listen up. Okay? Before we jump on to boron, do we have any questions with this? Because it gets really complex when we get to that 2p. Always got to complicate it, right? Yes?
So for like the bonding orders, would it be like equal for like lithium and sodium?
Yeah. You got it. Because what happens, right? Your highest orbital set is going to be the 3s.
Yeah.
Right? The rest of them are all filled.
Okay.
Okay. So now what we're going to do is we're going to build this row. And watch what happens. This gets tricky. So here's the world famous, NNU chemistry famous, NNU famous Dr. Einstein's smudge. You see that line right there? Over the years, that's been getting more and more accentuated. That's a special line in molecular orbital theory. Okay, so here's what happens. Let's take and let's draw a molecular orbital diagram for boron. But here's the problem with boron. Boron now shoves an electron into that 2p orbital. Okay? So boron, notice this, and the whiteboard's not quite tall enough to do what I want to do, so I'm going to make it kind of exaggerated. Notice boron, one boron is 1s2, 2s2, 2p1, correct? We're all comfortable with our atomic orbitals? Boron over here is 1s2, 2s2, 2p1. Again, you should be absolutely mastering that. That's no problem with our Aufbau diagram, where our electrons go, we know that. Here's what happens. When I have 1, 2, 3, 4, 5 atomic orbitals, 1, 2, 3, 4, 5 atomic orbitals, I have 10 atomic orbitals. So how many molecular orbitals do I have to have? I have to have 10. So 1s, 2s, 2p. Man, that's not very good board management. This one's really kind of hard because it gets a little bit dicey. Okay. Still not happy. Okay. 1s, 2s, 2p. 1s, 2s, 2p. So how many atomic orbitals do I have? 10. I have to have 10 molecular orbitals. Okay? So we already saw these. We have this guy and this guy, this guy. I'm just crunching them down. So this has a probability. This has a probability of here or here. 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 We call this the sigma 1s, the sigma star 1s. We call this the sigma 2s, and we call this the sigma star 2s. We all tracking? Okay. Here's where it gets fun. When you have 3 p orbitals, now stay with me. Please engage with me on this. What am I saying in spatial arrangement of these 3 orbitals? Why do I have 3 different isoenergetic degenerate orbitals? I already alluded to it first.
These give like 2 nodes for each orthogonal.
No, these all have 1 node.
No, okay.
How are,
One for each orthogonal.
I'm just asking how, yes, that's all I want to know. In spatial arrangement, there's an X, Y, and a Z. That's all they differ. Okay, well, yeah, all right. You speak a language I don't know. Okay, so think of this. As you have 2 pi orbitals coming together, notice, you can bring them together this way, right? As you have 2 pi orbitals together this way, you can bring them together this way. But if you're on the X plane, you bring them together head to tail. Notice how that's different. This should look similar to this, but it's going to look different than this, correct? X, Y, and Z. That's what this is saying, X, Y, and Z. So you have 2 that look the same. You have 1 that doesn't look the same. So our probabilities of our molecular orbitals are bringing these together look like this. Okay? These 2 are the pi 2p. And you can call that actually y and z. Okay? This is a sigma 2p. That's the one that goes like this. Remember, if I bring together head to tail, that makes a sigma bond. That's the hot dog. If I bring it together this way, that's the bun. That's the pi bond. If I bring it together this way, that's the bun. That's the pi bond. This was the hot dog. This was the sigma bond. So notice, I have a sigma 2p, which is different than my sigma 2s and my sigma 1s. And now I have my pi 2p, pi 2p. This one and this one should be degenerate or the same energy. Okay? I start with 10 atomic orbitals. I have to have 10 molecular orbitals. I do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Boom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Isn't that cool? So watch what happens when I populate boron. Boron. 1s2, 2s2, 2p1. 1s2, 2s2, 2p1. Okay? So here, what happens when I bring these two together? They what? They go to the lowest energy? Do they spin up, or would they rather be separate? What did Hund's rule tell us? Be separate. So it puts one there and one there. Now here's the aha of molecular orbital theory. Who wants to predict the bond order for B2? What's the bond order? What is it? Well, it's not really super difficult. Bonding, whoops, sorry. Fill all these in. They're all full. So it's going to be 2, 4, 6 minus 2, 4 divided by 2. 6 minus 4 divided by 2 is 1. So the bond order for B2 would be predicted to be 1, but here's where molecular orbital theory becomes amazing. Boron, B2, is paramagnetic, meaning if you put B2 in a magnetic field, it's attracted to the positive pole of a magnet. Oh, that makes sense, because these two electrons are unpaired. And a positive pole of a magnet would see that, and it does, experimentally. So the property is paramagnetic. Isn't that cool? And that's exactly what we see. Okay. Let's go to carbon. Carbon is 1s2, 2s2, 2p2, 1s2, 2s2, 2p2. So carbon looks like this. So where does carbon put those other electrons? Hey, John. Were you going to say?
Yeah, well, in the sigma 2.
Well, remember, it's going to put them in the lowest energy. Where's the lowest energy?
In the 2
By 2p. It's just going to spin param here. So there's carbon. So what's the bond order of carbon? Two, 4, 6, 8 minus 4 divided by 2 is 2. Would I predict that carbon would be paramagnetic, visible in a magnet, or diamagnetic, invisible in a magnet? Be diamagnetic. It's exactly what we see experimentally. It is diamagnetic. Okay. Well, let's go on. What is the electron configuration of nitrogen? Anyone? 1s2, 2s2, 2p, 3. Where does that electron go? Well, in the atomic, because of Hund's rule, it goes there. Okay? So where does nitrogen then put its next 2 electrons for its bond, its molecular orbital bonding? Tyson?
Would it be the anti at the top or
No, lowest energy.
the lowest energy?
Yeah, right there. Good. So There it is. So what is the bond order of N2? It's 3. Hey, that's kind of cool. That's one place. That's actually one place where Lewis dot structure actually works, right? Because we know that nitrogen from a Lewis dot structure actually looks like this. And they actually agree. Lewis dot structure gets that one correct. So Lewis dot structure and molecular orbital theory agree. What would I expect for its magnetism? Again, wait. Are there any unpaired electrons? There's no unpaired electrons. There's no attraction in a magnetic field. So this should be diamagnetic, and nitrogen's very completely inert in a magnetic field. Are we tracking so far? Because I'm going to complicate it right now. All I'm doing is going from 5 to 5. That's it. I'm filling them up the way we know the atomic, and I have to fill them up in the molecular. Shouldn't be that much more complicated than that. But here's where the world famous smudge comes in. You see the smudge? Something flips at the smudge. And here's what happens. As I begin to fill these orbitals, okay, stay with me. Boron, carbon, nitrogen, oxygen flips. See where the smudge is? Boron, carbon, nitrogen, oxygen. That's why the smudge is there. Because oxygen doesn't look like this. Oxygen looks like this. At the smudge, it flips. The 2 pi and the pi, the pi, this is the pi 2p x, or y, pi 2p y. This is the pi, or sigma 2p. They flip. It's this, it's this, and this. Okay, it's going to keep going. And you have to just trust me on that. So let's do oxygen and see what happens. So oxygen is 1s2, 2s2, 2p4. So now, because of Hund's rule and Pauli's exclusion principle, I do this, and I do this. I'm going to go ahead and put 4 electrons and 4 electrons. 1, 2, 3, 4. Right? Am I good? Oh, wait a minute. Did I jump too fast? Oh, yeah, sorry. Bum, 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 bum. Okay? Something's not right. I messed that up. Just a 2p4. There's 3. How's that work? It's good enough. Okay, so what I have, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right? 7, 8. I'm good. So what would I predict for my bond order for O2? What's the bond order for oxygen? 2, right? 2, 4, 6, 8, 10 minus 2, 4, 6 divided by 2 is 2. But here's where molecular orbital theory gets it right. What's its magnetism? Paramagnetic. And that's exactly what we see for oxygen. How cool is that? Okay, so it's paramagnetic. And so if you just continue on with the journey, what's fluorine going to be? Here's fluorine. What would you predict for fluorine's bond order? Well, again, we just put 2 more electrons up in the the anti-bonding, so F2 is going to be a bond order of 1. And what's its magnetism? You got it. And let's land the plane or crash the plane, however you want to look at it. If I bring argon, or excuse me, neon, what is the bond order for neon? 0. And that's exactly what we find. Okay? Now, great question that I think was asked twice. What happens when I don't have the same atom? Stay with me. So let's get rid of our electrons here. Okay, what happens? Actually, let's just leave these out. All right, I don't want you to think about this. What happens if I were to give you on the exam and ask you to predict the bond order for NO? Okay. Nitrogen monoxide. What did I just do? How did I complicate it? Won't have an even number, so I'm going to have a half bond probably. But more importantly, notice what I did. I picked one from both sides of the smudge. Who wins out? And what? Who? Why? Electronegativity. Bingo. So if I have an atom on the right side of the smudge, it has a higher electron affinity and electronegativity, therefore its electron geometry wins out. So if I gave you NO, it would mimic oxygen, which looks like this. So if I bring in the 4 for oxygen and the 3 for nitrogen, notice, stay with me, we have a couple minutes left. We have a minute left. No, a minute. Notice, how many do I have? 1, 2, 3, 4, 5, 6, 7. So I am, oh. So what would the bond order for NO be? Anybody? 6 minus 1 is 5 divided by 2 is 2.5. So NO is going to have a bond order of 2.5. What's its magnetism? It's paramagnetic. What would happen if I asked you the bond order of NO minus? Who do you think has the extra electron? Oxygen. Boom. Where does it go over here? Here. What's its bond order? It's going to be 2. Is it paramagnetic or diamagnetic? It's paramagnetic. Do you see how molecular orbital theory is so powerful and what it predicts? Dr. Lawrence could actually do oxygen to show you how over a magnet it goes to the positive pole. We should do that sometime. Do you? Maybe on Tuesday. We'll do that during lab. It'll be fun for them to see that. Okay, hey you guys, when we get back from Thanksgiving, we do have an exam in here. I'm just going to tell you they'll be heavily charged on chapter 9. Remember, chapter 7 and 8 are more trends. Okay? Size, ionization energy, electronegativity, electron affinity. Bonding theory is really the hallmark and the foundation of chemistry. This is important stuff.
Will you be posting a practice exam?
Yes, I will focus on practice exam. Yes.
Thank you.
It's Monday when we get back. Week from today. I know. Yeah, well, Thanksgiving is study for it. It should have been today. So you did get 1 extra. great study work. You wanted it today? So. Okay. Send an email. Yeah, I'll open it back up. Did you send me? Okay, I'll go back to you. I have no clear. Yeah. Yeah. Yeah, so remember it's bonding. So it's bonding minus anti-bonding.
Yeah, so what is?
So bonding, anything with an asterisk is anti-bonding. So this is going to be sigma 2p. This is going to be pi 2p, pi 2p. This is going to be pi star 2p. That's anti-bonding, exactly. It's above pi star 2p, and this is sigma star 2p. So bonding, 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 bonding. Antibonding, 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 antibonding. So 2, 4, 6, 8, 10. So 10 minus 2, 4, 5, 6 divided by 2. Cool?
Yeah, that makes sense.
Yeah, yeah, awesome.
And then, I know I missed some worksheets. Are you gonna post like any old worksheets?
I'm trying to get everything caught up.
Okay.
Lecture videos, worksheets, yes.
Okay.
Everything I've got, I'm trying to get online.
Okay, sounds good. I'll
Okay.
look for that.
Okay,
Thank you.
awesome.